Welcome back. Some of you who have watched some of the previous videos may realize that this one is pretty similar to a previous one where we talked about how to transform graphs. In the previous video, I just wanted to go through and show you how to use a particular file. In this video, I'm going to explain how each part of the equation of a couple of example functions, so probably a quadratic and then maybe a trigonometric like a cosine function, how each part of the equation affects the graph in a bit more detail. So rather than having you kind of go through an Explorer worksheet, I'm going to be a little bit more direct in this video for you. I am going to use a GeoGebra file that was displayed or shown in the previous video you may have seen on YouTube. And I'm just going to start off with a quadratic function. And again, this quadratic function is in vertex form. So if I come back to one of our notes in class and I go down to quadratic, I had a lot of information on this slide. We're just going to look at a few things in particular since we're looking at vertex form here. And regardless of whether you are in vertex form or standard form, or if for that matter even in factored form with a quadratic function, there's always this number out in front. We have the coefficient a here. It's a constant. It's a number. It could be greater than 1. It could be less than 1. It could be greater than 0 or less than 0. So it could be any number you want. And in fact, no matter what type of equation you're dealing with, you really kind of have a number out in front of your independent variable x that has a similar effect on most graphs. Not all graphs. It's not all the same. Exponential is probably a little bit different. Absolute value probably works very similarly to how the quadratic function worked. Cubic function works very similarly, that a term, as to how the quadratic function worked. Same as some of our periodic functions as well. So just in general, if you have a number, some sort of constant out in front of your variable, it generally serves to stretch your graph, to make your graph grow more quickly. So for example, if I go back to the quadratic function, and let's just say that I typed in this equation into my calculator without the 2. Well, for every x value, you'd get out a particular y value. But with the 2 in front, what it does is it doubles that y value. It makes it grow much more quickly. So without the 2, you would have a graph that maybe has the point 1, 4, for example. With the 2 in front of the parentheses, instead of having the ordered pair 1, 4, you might have the ordered pair 1, 8. So that value of 2 makes the graph grow more quickly, and you can see here in our GeoGebra file, we have a 0.3 in front. As I increase that value, our graph seems to shrink. Well, it's not really shrinking. It's not getting smaller horizontally. What it's doing is stretching vertically. So for every particular x value, it's being multiplied by this factor out in front. And as that factor grows, so does the result of that multiplication, resulting in a larger y value, and that's why your graph appears to get smaller. Or I should say shrinking horizontally, when in reality it's not what it's doing. It's stretching vertically. As this number gets smaller, the opposite happens. And if it becomes negative, the graph flips over. We call it a reflection over the x-axis. So if you have a negative number in front of your variable, a lot of times that will signify a reflection over the x-axis. And that works, again, similarly for a lot of these different types of functions. So an absolute value function that is now flipped over the x-axis with that negative value in front. And as you get further away from 0, you can see how that graph appears to become skinnier, but again, it's really stretching vertically. Let's say I was looking at one of our trigonometric functions. Let's do the sine function. You'll notice that, well, this one's shifted over, so it's hard to tell, but if it weren't shifted over, and maybe I can move this over for a second, you can see again similarly how this has, let's go to 1, sorry. You can see here now with a negative a value, the sine function is coming down through the origin. If you were to graph sine of some number in your calculator, you would normally see it go up through the origin. So again, that a value flipped it over the x-axis. It was a reflection over the x-axis. So that's what that number in front of the exponent does, or excuse me, the variable does. If If I go back to quadratics, you may have noticed that we also had some numbers down here, a plus or a minus after the x. And again, in a lot of our different types of functions, this works similarly where it represents a horizontal shift. So we move the graph to the right or we move the graph to the left. One of the tricks about moving the graph to the left is to recognize that with a plus sign after the x, what you're really doing is subtracting a negative. This is really minus negative 1.4. The number here isn't 1.4, it's negative 1.4. That's why the graph is over here on the negative side. It's backwards of what you might expect it to be. And so you just have to be aware of that fact. And that works the same in, again, all of our functions. Here's the sine function, plus 1.4, even though our graph has been moved to the left. Even though we have that positive 3.2, 3.3, we're shifting the graph to the left. So again, anytime you have your variable and then plus or minus some sort of number inside of parentheses like this, it generally will serve to shift your graph horizontally. And we can see it with all sorts of different types of functions. Here's a radical function. You notice the radical function is going down to the negative values because you have a negative 1.1 in front. So that graph has been reflected over the x-axis. If I make that a value positive, we're up there. And if I make it large, you can see the graph grows more quickly. It's being stretched vertically. But what we're looking at right now is this h term, the one after the x. And again, you can just see that serves to shift the graph left or right. Now, outside of those either parentheses, in this case a radical sign with the x minus 1, sometimes you'll have another number like this. And that's a vertical displacement or a vertical shift of the graph. It just moves the graph up or down. So if you have a number after your independent variable that's not attached to your independent variable in any way, it's not in any sort of grouping symbols with your independent variable, but it has a plus or a minus to it, that's generally telling you the graph is being moved up that much or down that much. And this one, the minus signs work as you would predict. A negative 1 means the graph is moved down 1. So it's not backwards like the horizontal shifts may have appeared to be to you. And what this is really doing, these values, they're saying, hey, evaluate this whole equation first for the independent variable, and then just add a quantity to it. And since you're just adding a given constant, a given quantity to your function, it just moves the function that amount up and down. Now, there are a few other terms that we may come across when dealing with the equations. With a lot of the equations you dealt with in your early years of math, and we're looking at, linear, for example, quadratic, maybe even cubic and exponential, these values all kind of work the same. There's our slope, it stretches the graph. Here's our horizontal shift, it moves the graph. Here's our vertical shift, up or down, also y-intercept for a linear function. So for a lot of these, they have the same effects when we're moving the graphs. Here's exponential, there's x with a number, so that's going to be a horizontal shift. In this case, the other thing to be aware of with a exponential graph is this rate or slope. So with an exponential graph, this is like that kind of the value in front of the x. Now, we still have this a term here. What that a term really does, it helps affect where the graph starts, not necessarily how much it's increasing by. This is more about where it starts. Over here, this 1.5 is how much it's increasing by. So that's a little bit different than what we saw with the quadratic function or the absolute value function, where that number out in front really stretched and affected how much that graph changed by. Exponentials are a little bit different. So a few of these functions are a little bit different than what you saw in those first few examples. That's why hopefully you paid a good amount of attention in class, and you've gone through and looked at some of these files that are up on Colab, that you've played with this GeoGebra file, so that what I'm saying isn't completely foreign to you. Also, I had to pause the video right there, so hopefully that transition was okay for you. The last thing I wanted to take a quick look at here with you is probably a trigonometric function, sine, tangent, cosine, and for the sole reason that they also have this b value here, which is a little bit different than what we've seen in some of the other functions. So you can still see they have a horizontal shift because there's a number being added or subtracted to my independent variable inside of some grouping symbols. There's a vertical shift over here because there's a number being added after all these other operations occur. And so that's my vertical shift. You can see the graph is being stretched vertically, which is different than a vertical shift. A vertical shift is just moving the graph up and down, which I guess maybe I should show you. Whereas this value in front is a stretch of the graph. The thing that's different about a sine function or a tangent function or a cosine function is the fact that we also have this b value. That's what affects the horizontal stretch of a trigonometric function. A larger b value in this case makes the graph compress horizontally. A smaller b value in this case makes the graph stretch horizontally. A b value of 1 would make you have a period of 2 pi. So between where it starts and until it's back to that point would be about 6.28 radians. And again, you'll learn a lot more about that when we get to our trigonometry unit. But the general information here, and again, hopefully you've gone through and played with this file already, so what I said here in this video wasn't totally foreign. Hopefully you've gone through and you've looked at this file up on Colab that has all of this information written out on it, so that what I've said hasn't been totally foreign to you. But I just wanted to kind of go through and highlight what some of these specific values did. The A values, B, H, K, horizontal shift, vertical shift, and just kind of show you and walk you through a few examples, just in case you had any questions. Again, if you have questions, a video isn't quite as good as actually being able to ask a teacher or ask a friend, so please make sure you stop in and ask so that we can help you. And with that, thank you for watching, and we'll see you again next time.